Wind Energy Center.
Good morning and welcome to the COO seminar. The speaker today is Professor Mark Balas. He is the Guthrie Nicholson Professor of Electrical Engineering and the head of the ECE department at the University of Wyoming. He has a PhD in mathematics, an MS in electrical engineering, an MA in mathematics, and a BS in electrical engineering.
Okay, good.
That it?
You don't have to do any more.
Okay, so at the request of our speaker, I'm stopping our introduction. You're free to go to our website to see a more detailed
and boring
bio.
and boring.
If you're joining us by the simulcast link, I want to point your attention to a Skype contact. It is crew_collaboratory, crew, C-R-E-W in caps and the rest in small letters. You can, while our professor is giving a talk, you can give your comments and your questions on chat. I'll be moderating it and I'll present those questions at the end of the presentation. That goes for our physical audience as well. Please hold your questions until the end of the presentation. Without further ado, Professor Balas.
Thank you, Sid. That's very kind of you. I'm glad you didn't read the whole thing. So I'm assuming I'm on the air and everybody can hear me. And if there really is a question, like if we look at something here and you say, geez, I don't know what he's talking about, by all means, you know, you can ask that question. If you want to ask kind of longer, more elaborate stuff, I think we'll wait to the end. Does that sound reasonable? How do I get this? Do I just hit this? No? Can I? S5. 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 Okay. I mean, I can start it from the slide sorter, but
It's the hardest part. Sorry, that's it.
is it getting the thing? Yeah, that's what I was going to do, and that I knew how to do. Thanks, though. Thanks. Turn the lights down. Can we turn these down? How's that? Is that better? Is there more? I don't know if I can turn them down more. And now we have some other idiot thing here. Go away. Oh, dark and dark. So, yes, so Sid introduced me, and I'm from up in Wyoming. I used to be down here. I used to be at the University of Colorado Boulder. But that's probably not a good thing to say on this campus, is it? So I always want to mention the group I call my wind kids, because many times you know some of them, since many of you are working in this wind area. Susan Frost, who is also listed as a kind of a co-conspirator here because we've done so much of this adaptive control work together that I want to put her on there. But she's at NASA Ames, Alan Wright at NREL, Jason Yonkman at NREL, Maureen Hand at NREL, Katie Johnson, who may be out there in the ether somewhere at the Colorado School of Mines, Carl Stahl, who is even farther away in the ether at the University of Auckland, Darius White at Embry-Riddle out in Florida, and my two current PhD students in this area, Kaman Tapamagar and Nailu Lee. So without them, we get nowhere. And I'd like to start out with this thing, one, because I'm a big fan of Freeman Dyson, the last of the great quantum mechanics people. And but this statement by Dyson, it's not the theories about stars, the actual stars that count. And I like that, especially because he's a theoretician too. And so I've spent an awful lot of time even being a theoretician, but working on some of this panoply of things here, solar power station, launch vehicles, wind turbines we're going to talk about, precision structures, and evolving systems. And my view is that these are the things that give rise to the new theory. New theory generated all by itself is, as far as I'm concerned, is sort of an abstract waste of time. Not everyone agrees, of course, but I sort of feel like when you work on these serious things, they cause you to have to go back and modify the things that you already know. And consequently, that's why I like Freeman's statement. The other thing is, you may not know where Wyoming is. A lot of people don't. And, but we're just a little north of you and about 2,000 feet higher. And there's a little thing there that points to where the university is in Laramie. So we're about 120, 130 miles away from you. No, less than that, 70, maybe 70, 75 miles away. Makes a lot of difference, though, because we get snow when you don't. And the other thing that's good about us is we have the best-looking license plates in the world, okay? With Steamboat on there and, you know, riding that thing, is nobody comes close to us. But just so you know, some of my friends back east think that Wyoming is in Canada. So just a little geography lesson. Here's just some stuff. You can't read it. I didn't really want you to read it. You can read them someday, but these are maybe 10 papers that various of us have been working on that have to do with this talk on adaptive control of wind turbines. And so, you know, there they are. So long. The other thing I'd like to do is introduce the Wind Energy Research Center, which I carefully named so that it would come out to match this particular thing. So those of you who are cinephiles and know about Quentin Tarantino and Reservoir Dogs would know, let's go to work. Okay, but John Naughton and I are both the, you know, we're the co-directors of this Wind Energy Research Center. Some of these slides are so canonical that I'm sure you will have seen them a lot if you're studying anything about wind, and I don't want to dwell on them because there's other stuff I'd like to tell you about if I possibly can. So I'll just sort of zip through it, but why are people interested in wind now? Because the cost has come down substantially, okay? And, you know, that's the real heart of it. And if you start looking to see where are the wind resources in the United States, they're almost always in places that are far removed from the centers that actually need the electric power, okay? So you can kind of see that sweep of things there, and you can kind of see us up there. Wyoming, we got a lot of wind. We don't actually know what to do with it. We'd love to get rid of it, actually. And so if wind turbines would help that, that would be perfect. But the other thing to note is where the real concentration of wind energy is on the coasts. Okay? It's offshore. So if wind is going to turn out to be, as we'll say later on, 20% of the U.S. power and all that sort of stuff, if that's really going to happen, we're going to have to develop offshore. And offshore is a much more complicated environment than the onshore kind of stuff that we're all used to. But just so you can see that, so that, I guess I can't point to it. I can't point to it with the electronic people, right? You can't see me if I go over here, can you? Can you electronic people? Can they see me? Okay, over here maybe. But kind of looking up in, oh, God, I shouldn't have touched it. Up in here, okay, these are generally load centers here in California. And so you can see that the offshore stuff is not far from the load center. But it's also where a bunch of rich people are that don't like you to put wind turbines in their point of view. Let me take that from you. Thank you, Sid. That's great. I'll screw this up for you too, but what do we do here? Oh, that's actually easy. So, oh, now, God, now we're off the thing, aren't we? Here. Okay, I don't know. Can I get rid of this? Yes. No. Locked up. Ah, thanks. Thanks. Thanks for the tip. So anyway, and now we have another thing here. Let's see if we can go to the next slide. Ah, hooray. Okay. All this smart stuff can totally outsmart you. So this is the rich guy, T. Boone Pickens. And some time ago, he said wind power should account for 20% of the U.S. energy needs. And then everybody started saying it. Okay? After that, you just couldn't go any place without hearing somebody say 20%, 20%. 20% is a gigantic amount, to tell the truth. And whether the real rich guy is still interested in this is a little hard to tell. Okay? So I say when real rich people start telling you things, you should always be suspicious and you should watch your step. But, you know, if 20% is the goal, okay, let's see if we can live with that. The other thing is, when I first got into this stuff, which is, you know, many years ago actually, I've been in this now, I've been maybe 10, 12 years, I've been doing that long before anybody was really all that hot about wind. Everybody loved wind. You couldn't go any place without somebody saying, "Oh, we love you. Wind is so great." Everybody would just follow you around and all that stuff. As time has progressed, we see that not everybody loves wind anymore. And here's just a couple of things that we might look at. Of course, you can see some turbines on fire. They don't usually catch on fire, but when they overheat, when the gearboxes burn up and stuff, yes, sometimes they look like this. So that's an issue, and I put a few of those. Lightning strikes them all the time, stuff like that. This thing here, I think, is a trumped-up photo because I think that somebody's used like a long lens here and focused on the turbine, but it's quite far away from this building. This comes off of one of those eco websites where people want to tell you everything that's wrong with anything you want to do. Here's a serious problem, even though this is, I think, a British town somewhere. But how do you get those gigantic turbine blades on a truck or on a railroad car and get them around the curves and the radii in the highways or on the railroads? So that is a serious problem, and you don't want to segment them if you can help it. Here's a problem that is serious, although I think there are a lot of things people can do to get around it, and that's the whole issue about raptors roosting in the high turbine areas and wanting to stoop or swoop down to capture things that are flying by, which they like to do. The other thing is bats have turned out to be kind of an issue. Apparently the pulse shock waves from the turbine causing some difficulty with the bat's internal organs and stuff, so that's, I guess, an issue. This one was one of my enjoyable ones. This is the radar signature problem. This was, I think, based on turbines that were set up in the North Sea, and the real problem was as you begin to look out across with your radar, as you're scanning the horizon, the turbines cause a certain amount of chaff, a certain amount of interference. And I assume that's because in Britain they're afraid that the United States will attack them and that we'll fly in under the cover of our wind turbines in the North Sea. But could happen, I suppose. You never know. Here's also my favorite crazy one, just to share with you, is that people had said this somewhere. They said, tentacled UFOs spotted days before a turbine was destroyed. Family has described seeing tentacled flying objects in the night sky just days before a wind turbine was supposedly wrecked by similar-looking UFOs. Okay, I don't know. If you see the old version of the H.G. Wells book, if you see the old film made from that War of the Worlds, you'll see things that do sort of look a little like wind turbines. Okay, I doubt very much that the aliens are coming in here and saying, "Oh my God, there's us. We've got to kill them." But you never know. I mean, people have got some great ideas. Here's the most canonical slide I will show you. If you haven't seen this slide, you must not have been listening somewhere. This slide is so much the regular canonical thing that everybody uses that really it should be set up in a book somewhere, and we should just all refer to it. This is an upwind turbine. We're looking at the at the rotor and the wind flow across the turbine blades first, and then passing through a gearbox. The gearbox turning a generator, and primarily that's the essence of a large wind turbine. Some turbines are downwind, and so they would be turned 180 degrees, as I'm sure that most of you know. Just some basic stuff there about horizontal axis wind turbines. I'm not going to talk about any of the vertical axis stuff or any of that kind of stuff, any of the oddball kind of things. These are the workhorses, and these are the things that people are building bigger and bigger. Considering largeness, height comparisons, people often call these things windmills. This is a windmill. Okay, actually, it isn't even that. It's a thing that pumps water to feed cows and stuff. But it's not like Grandma and Grandpa's windmill. This thing is not a windmill. This is a wind turbine or a wind machine. Okay, it is nothing like this thing down here. And you can just kind of see some general scaling here. And here would be Grandpa, although my grandfather was never 6 feet tall. He was about 5 feet tall, but he probably could have knocked this thing over if he'd have tried hard enough. You see a Boeing 747, kind of the wingspan fitting into the blade span of the turbine. Some people think that might be a real good use for the Boeing 747 too. Here's another little better kind of idea of the thing, just sort of looking at how turbines are increasing in size as we move up from single turbines that are running at a little bit more than a megawatt all the way up to what could be the 8 to 10 megawatt power range for a single turbine. And just some stuff here. I think Susan stuck this in. Is kind of useful. Wind speed can increase by 20% with a 10-meter increase in height and blade span. Largest turbine in production is a 5 megawatt one, probably now. And I don't know where that turbine is. Maybe you do. And just some stuff about the wind power being proportional to the cube of wind speed. But those are all canonical things. What are the wind energy research issues? Why should anybody be concerned? Well, wind turbines break. Okay? They don't last as long as they should, and they cost a lot of money, and they break down. Some time back, a new thing was done at the NASA Ames Center, is that NREL put up a turbine in a wind tunnel out at Ames. This has never been done before. You know that every airplane goes through some period of time when you have it in some version of it in a wind tunnel. Turbines never have. This one, and they said, okay, give us all that numerical stuff. Give us all that numerical stuff that you all do in flow control, comp fluids. Give us the whole thing. Tell us what things should look like. And lots of different people did. NREL invited this, and lots of people did. 100% error was the best anybody could do. 100% off. Okay. So, and some of the things were like 1,000% wrong. So the comp codes weren't all that good. You know, a lot of things weren't really modeling the turbine. Everybody panicked, and now they're all probably back at the desk scratching and changing codes and all that sort of stuff. That's maybe, what is that, 7 years ago now? Maybe 6, 7 years ago.
About 12.
More than that?
About 99.
Oh, was it that far back? Okay. I remember Maureen Hand, who was a student of mine, was working on the thing. So, wind turbines still fail. Most of the times the exact cause is not completely known, but the primary failure mechanisms are the gearboxes and the blades. Okay. Blades break off, gearboxes burn up, and then this little situation here, which is pretty exciting, is when the whole thing comes down and the tower breaks down. So, I'm not going to talk about wind farms as generating stations, but I think if Katie Johnson hasn't talked about this already, I'm sure she will at some point. So she and some other people are more interested in the whole thing as a generating station. I'm much more focused on the actual turbine itself. And so, you know, future trends, we've already sort of talked about it. Large megawatt turbines placed on very tall towers. Softer, more flexible compliance systems. I like to think of them as maybe being more agile. Increased likelihood of structural dynamic responses with aerodynamics failing, and multi-sensor kinds of controls being used. So some of the stuff we're just going to talk about at the bottom of the page there, and what you could do. Typically, you can control the blade pitch. You can control collectively or individually. People don't do much with individual yet, but they are moving in that direction. You can also control generator torque. Here are just some pictures of actuators and stuff. Here's pitch motors that could individually control the blade pitch. And here's some ideas of sensors. Typically tachometers, sometimes accelerometers embedded in the blades. Although the blades take an awful lot of beating in the weather and stuff, so things embedded in the blades tend to not be embedded for very long. Electric power sensors, but of course they drain off a certain amount of power when you use them, and strain gauges and such. One other thing that I want to mention, and that will come up again a little bit later in the talk, is wind speed sensors. The typical wind speed sensor is a cup anemometer that is stuck on the turbine someplace, typically on the back of the nacelle. Okay? They break off all the time. They're really junky. They don't cost very much, but they don't work very well either. And so, in fact, you could buy one at Radio Shack for about 12 bucks. So what people are thinking about is other kinds of sensors. I'm not here to sell anything. I just, you know, I'm thinking a little bit more about LiDAR because there are people who have asked me to think about LiDAR. And people are doing that. I think Katie Johnson, for example, is doing a bit about LiDAR. And let's see. There's other people, but I can't think of who. And so we're sort of looking at this LiDAR issue too. LiDAR is very precise indication of a lot of detail in the wind field, because in any kind of a wind field, there's a lot of dust. Okay? There's typically a lot of dust. And so you're reflecting the LiDAR off of that dust. But you have to look pretty far out ahead of the turbine. You can't look close to the blades, which is where you'd really like to know what the wind speed is. Simulators, there's lots and lots of different simulators, but FAST is the one that the National Renewable Energy Lab uses, and it's a multi-body type of thing. And I just have you look at this list, and you can see kind of some, you know, like Tom Kane is sort of the method, is the brains behind it. But I think this is the real answer down here. Well accepted by government and industry with field test validation. So if you're not doing things in FAST, you're probably not doing things that NREL cares about. Okay? It's just, it is like that.
It's also available for free, right?
It is available for free. You can go to the NREL website and you can actually use their models, the ones that are posted there. Here's again another canonical slide about wind power, and it's just saying, you know, we look at 3 regions of turbine operation that the turbine is divided into. Region 1 is sort of the spin-up or the startup point, and we're not very interested in that. You just have to have a certain amount of wind in order to move, you know, in order to move this gigantic thing. And but at some point there's a cut-in, and there's a wind speed cut-in, and then there's a period where the turbine is generating a curve here that is like the ideal power. This is the ideal power, supposedly, that you could extract from the wind. It goes as the cube of wind speed. Okay, and so what you see is a kind of a similar curve here. So you're extracting as much power out of the wind as you can. Then right here in region 3, you switch over, and now what you're trying to do is just regulate the turbine and have it run, you know, at a constant speed if you can, and produce fairly constant power. Obviously, nature doesn't let us do that with a wind turbine, but these are the basic ideas. And you know, something like this that had a kink in it right here would never work. Typically, what a turbine does is kind of work its way up this thing and then bounce around a little bit up here. So you maximize power generation in region 2 if you can, and you maintain rated power in region 3. So you want to track something here, as we'll see later, and you want to regulate when you get into this region. And we'll see that you do actually with different actuation in the 2 regions too, and you want to match them up. And some people call this middle region, this kind of transition region, region 2.5. Okay, where you're switching from 2 to 3, or maybe as the turbine comes along and the wind dies down, you drop back into region 2. Okay, so these 3 regions are all important areas for us to do control in. Another canonical slide, which again, if you haven't seen it before, it's probably somebody's done something wrong. But the standard thing, I don't know what that is that's in the middle of it there, but some helpful thing, I'm sure, from Microsoft. But anyway, this is the fundamental dynamic equation. And basically it says that the moment of inertia times the angular acceleration of the rotor of the turbine is equal to the difference between aero torque and generator torque. The generator is being turned, so it produces a back torque, and the aerodynamic torque is what is driving this thing. And the thing right under it is the fairly nonlinear aerodynamic torque equation, which goes like the square of wind speed, and some other things, which are tip speed ratio and collective blade pitch. The idea here being that if you could somehow match the generator torque with the incoming aerodynamic torque, if you just match those 2 things up, then the right-hand side would be 0 and you'd run at a constant speed. Okay? So that's the fundamental idea here. It doesn't work. It isn't the way things really happen, but it's a nice place to start thinking about it. And that's what makes this such a canonical thing. Everybody know what tip speed ratio is? The ratio of the speed of the tip of the blade to the wind that's flowing across it. And why people use that, the only thing I can guess is that every fluids person I ever talked to said, well, we like things that are dimensionless. Oh, okay. So tip speed ratio turns out to be a dimensionless quantity that I guess turns out to be useful. I'll buy that. But somebody said to me, well, couldn't you control people, make everything dimensionless? We could. We could just divide it by a bunch of things, but it wouldn't tell us a thing. Here's a picture of why the problem gets complicated right from the beginning. This is the so-called torque curve, that torque coefficient curve, and you see how highly nonlinear it is. The other thing is, these are just approximated things. These are just polynomial fits to data. Okay? There is no thing here that says underlying exactly. You know, it's like Newton's equation or Navier-Stokes or something like that. No, no, these are just curves that are fitted to data. And to do this, you have to measure them you know, for various things. So people have a collection of these. NREL has a bunch of them. But just to see how nonlinear it is. And you might imagine you want to operate right up here on the top because you get the maximum torque right here. But the problem is you can slide off of this thing with little variations in pitch angle and tip speed ratio. You can kind of slide off the front or the back. So slide off the back, the blades stall. And that's not such a good situation. Slide off the front is a little bit better. So really you want to kind of operate kind of around this ridge line here, if you can. And that's just, that's the rigid body thing with no compliance, with no gearbox, with no anything. That's just that basic equation operating. Here again, I'm just saying pitch control wind turbines in region, I love that little thing that's in your way, but says that in region 3, we're regulating. We're just trying to regulate things. We don't want this thing to overspeed. We don't want to burn out the generator. We've got a little bit of room. There's some headroom, as they call it, that we can move around in, but we don't want to have this thing really overspeed as the wind really picks up. And as the wind dies down, we slide down into region 2, and so now down there we're tracking something. We're tracking a desired tip speed ratio with the actual tip speed ratio. So we're trying to do a tracking problem there. Up here in 3, we control with blade pitch, collective or individual. Down here, we're actually setting the blade pitch and we're controlling generator torque. Okay? So again, these are probably things you've seen a million times and maybe they're totally boring. They're actually getting to that point with me to be totally boring. But so here's just that what we call the one-state model of everything we just talked about. And oh, okay, sorry, I can't. I have to put my glasses on even to read what it says. It probably says Mark, tough luck. Thank you. All right, thanks. And so, you know, you have to remember that it's only been a few years since I thought computers were only useful as footstools. So, you know, I've come a long way, really. So, the one-state model. And in the one-state model, you're going to do what everybody does, every course in control, linearize about a point. Remember, nobody can see this. Linearize about a point, you know, on this torque curve. And that's where you're going to try to run. But of course, you'll slide back and forth, up and down these things, and vertically as well. So you'll move around, but that's where you linearize. Here's a first one-state linearized thing that we just talked about. What's useful to think about here is that we are going to control with the delta blade pitch. We are going to try to control the delta wind speed, because if we can keep the wind speed constant, okay, and we multiply the wind speed by the constant generator torque, that's approximately the amount of power. Some losses and so forth, but that's approximately the constant power that we get out of it. But we're going to be in the presence of a shifting wind speed, so a delta wind speed. So we're going to have this disturbance in our face all the time. So here's the one-state model, just what I said, the control, the disturbance, and here's typical test winds. Test winds don't look like real winds, but they're just sort of staircases to look at, you know, to look at kind of what the turbine would behave like, just as a starting point. We'll also look at turbulent behavior as well, turbulent inflow. But just a staircase will give you some idea of how things behave. So you think about what should you do for this simple problem to control it? What should you do? Everybody who takes the first course in the undergraduate course in controls would be able to solve this problem, because you look at this and you say, I'm going to think of the wind as changing in a stepwise fashion, so I want to reject step disturbances. And I want to put some feedback around this first order system, and so what would I do? PI, proportional integral control. That would be the thing that you would do. That would be the guess, and sure enough it works. Okay? And in fact, people who don't know anything about control actually use PI control. What they do, though, is they run a simulation and they probably sit around with a, you know, they don't have graduate students like we do, you know, to do all this dirty work. So they must have employees somewhere who sit around twiddling these two gains until they get everything to work right. Right? Is that right? Yeah. Is that what you guys do? There must be some low class of people that you can, that, you know, that are sort of like grad students that you can torture in some horrible way. Yeah, it's an understood thing. I guess I've probably revealed that now. Sorry. So grad students thinking about this, guess where you could be? Okay? You could be working on this stuff too. But most things work here. I mean, there are a lot of sophisticated things that people have proposed now. I mean, you know, I'm an editor for a couple of wind journals. God, we get a flow of stuff now with, you know, with all kinds of hyperactive controls and stuff like that. But everything works on this particular situation. And this is the way it should look, is that you should maintain rotor speed, okay, with little hiccups where the steps occur. Okay, so what you don't want is you don't want to follow these steps, so you don't want the speed to increase in a staircase way. But here's what happens if you just look at the simple dynamics and you add the drivetrain torsion mode. Okay, so you say, I've designed this thing for the most basic equations, and now what I'm going to look at is I'm going to introduce the drivetrain torsion. There's a compliance in the drivetrain. Okay, and later on we'll see some of the frequencies for that, but and some of these other resonances. As soon as we put it in, there's two different things running here. Let's see, the red is atoms, which is a different kind of simulation tool, and fast is this thing here. But what we see is this controller we just got through designing that works all the time and everything is suddenly unstable, okay, because of that mode, okay, because of that one mode. So you're going to have to start thinking about those things. And I think this is the perfect aerospace problem, because you have aerodynamics, you have structure, and you have control. Okay? All of those things are just the standard elements in every aerospace system, whether it's air vehicles, whether it's space vehicles, or whatever. And I've tried to sell this to aero departments and stuff. I used to work in one. They weren't the least bit interested, but it is what it is. This is what the wind field typically looks like. There will be a certain amount of shear. In other words, there's some slowing down due to the ground effect as you get closer to the ground, so there's a certain amount of vertical shear. Okay? That's somewhat predictable. And then there may be some variations on top of that. But the other thing is that the fluctuations in the overall speeds here typically do go like this stepping, like this staircasing thing. So that's not a bad way to look at it. Here's an example of some very unsteady inflow behavior called the low-level jet phenomenon. How many people have heard of low-level jets? Okay, so the experts have heard of it, but you forgot to tell your students? What was that? Don't let them know. Let them know that it's all easy right up to a certain point. This is some work that Maureen Hand and Mike Robinson and I did on the low-level jet thing. What we were interested in, you don't have to, in fact, I couldn't even read you through this whole diagram, but you don't have to look at all of that. You just have to look that there's a point here where things kind of go crazy. And these are vortices that have an impact upon the blade disc. And what we were trying to do is see, could we, and this is just numerical, could we fly through this? In other words, could we mitigate the effect of low-level jets? Because right now what happens when low-level jets show up, which are kind of in the evening, what they do is they shut down the turbine. Okay? I mean, they just kill it off, so it's not generating any power. And the jets don't show up in some kind of steady state way, so you'd like to kind of pass through or fly through the transient, and then on the other side of it, you'd be, your turbine would not have been broken, and you'd be able to go on. Some control design ideas. PID here, where sometimes instead of, along with PI, here's PI, you add some derivative in order to increase the damping in this thing. That's pretty standard, and people use that all the time, and they twiddle the gains and so forth. There's a lot more straightforward and analytical ways to do it, but by and large, I don't know that people do that. The kind of stuff we were interested in when I came to this thing 12, maybe some years ago, when I got into this, just to use kind of ideas of linear time invariant and also linear periodic state space approaches. And this is a so-called model in the loop, where there's an estimator that has a model of the plant in it to some level, and creates its control. And this controller can anticipate things from that model that the PID stuff cannot. And so, what is it? Oh, and adaptive. Yeah, we'll get to adaptive. And so the fundamental idea that I chose to bring to bear here was this idea of disturbance accommodating control. That down here at the bottom, here's Carroll Johnson, way back in the 1976, so much earlier than that, he was thinking of this idea. Is if you said, I've got an unknown disturbance which in this case is variation in wind, passing through a relatively well-known dynamical system, which is not absolutely true of a turbine. And we can look at the measured outputs. Could we somehow estimate the inputs, okay, without inverting the plant? You don't want to invert the plant. Plant here might turn out to be unstable when you invert it. So you don't want to do that. And so we began using this. I've used this disturbance accommodating stuff in other places, but we began using that here. And what you have to do is you have to model the disturbances in some way. You have to kind of guess what their wave shape would be. The simplest one we can think of here that matches with how wind turbines behave is just to think of steps, okay, to think of the disturbance as steps. Then here's a way to think of a unit step, to think of it as an amplitude multiplying by a basis function, which is just 1 everywhere. Okay? So that's sort of the simplest thing. You can have more complex models. You can also model vertical and horizontal shear as sinusoidal. And now what is happening is you're saying, I have some idea of the sinusoidal frequency. So I have some good guess of that, and I will use that to model this thing. But all of these things are really predicated on the idea that you could have some guess for what the input is. Now, another route that people use, hey, treat it as a stochastic process. I don't know, maybe if you're doing that, but every time anybody that I know has done this, it's been a disaster. Okay? Hasn't worked at all. We don't know the covariances of this, of the aerodynamics anywhere near what would be required to make a Kalman filter that would care one way or the other about this. But it's possible to make filters that respond to steps or respond to sinusoids of given frequencies. It's possible to include that. And that's what we intended to do. So recall the one-state thing. We're looking at the variation in rotor speed. Now let's move to something more complex model. This is a 7-state model. It includes the tower fore-aft motion, which is kind of this leaning and rocking forward and back. Okay? The blade flapping in and out of the rotor disc. Okay? But it doesn't have the edge bending, and it doesn't have the side-to-side in the tower. It also has the compliant gearbox. So it has the compliance in the gearbox. So this is 7 states, and just taking a look at how this stuff behaves. Here's some idea of what those frequencies are. Drivetrain at about 3.5 hertz. Blade flapping at about 2. And the tower fore-aft being typically the lowest frequency, which is around 1 hertz. That's a pretty slow movement. I've actually watched turbines that are perfectly well generating power and stuff that have been nodding back and forth. Okay? You can see this. Okay? I was out, it's now GE Wind, but it used to be Enron, or Zond actually, and I was out at Zond out in California in Tehachapi, and you could see that there were turbines that were operating there that had this thing. It doesn't impede the power generation, but it sure does deteriorate the tower. And the towers eventually come down if you have too much of that. So just an idea of those frequencies. Here's like looking at a 5-state and looking at a 7-state control, and you're looking at atoms and fast and stuff. I don't really want to look at the details, and I don't want you to either. But just to say that this was a foundation that Alan Wright and I kind of provided a long time ago for this work. We actually have tested, let me just put the test thing up there, on the so-called CART, the Controls Advanced Research Turbine at National Wind Technology Center, part of NREL in Golden. And we've actually tested some of these controllers that we just looked at on these things. I think this is part 1 of this thing, and I think there's at least 1 or maybe more of these test things that Alan Wright and Lee Fingers have done. But this for us was really a great thing because too many times you never get to actually test a real wind turbine, okay, unless you own it. And once you own it, drill a hole in it and throw away your guarantee. Right? I mean, that people are doing that, but you're not going to take a real production line turbine and start drilling holes and sticking things in it. But so there's that. The last general topic I want to touch on is the thing I said at the very beginning. If you're going to get wind energy, you're going to have to go offshore. Okay? And typically that's going to be in the northwest and in the northeast. So you're going to put things out in the water. And you're going to put them far out in the water. They're going to be much more like these floating things, maybe not even with any kind of attachments to the seabed, that they may just be floating around on a barge. very far out. As people have complained about this, I suppose there's always a complaint. You're lowering my property values on Martha's Vineyard if you put a bunch of turbines. But the turbines are really going to be so far out that what they're going to look like as they turn, they're going to glint. They're going to actually look kind of pretty as the sun comes up. Okay? I mean, they're not going to be that bad. It's not like these oil things that are right, hey, where I swim is where we drill for oil, just offshore like in California. So I'm not saying that this is all perfect and there's a perfect answer. Believe me, I know that as an engineer, everything has trade-offs, doesn't it? I mean, do you want the energy? Then it's going to cost you something, right? If you don't want it, that's okay. Turn off the electric blanket. Don't use the washer and dryer anymore. Don't make any more coffee, okay? That's the way to handle that. But I don't see people doing that. What I see people saying is more and more demand for energy and less desire to have the problems that energy creates. These things create a lot less problem than coal-fired plants. Here's just another thing, give you some idea. Depths beyond 30 meters, new foundations. But I think people are even now talking about the floating barge idea and actually using differential blade pitch to move the barge around. Okay? That's kind of a nice, cute idea, isn't it? Differential pitch and yaw and stuff. So floating platform is going to be the issue. And my student some time ago, Jason Yonkman, in his PhD thesis, this is my quote from his thesis, PID can't do it. Okay? He tried it, everybody tried it, and they couldn't use PID controllers to actually operate floating barges in a moderate high sea with, with fluctuating aerodynamic wind. Okay? Couldn't be done. So you're going to have to do something more sophisticated. Turbine dynamics, not accurately known. Yes, that's true. Unsteady aerodynamics, not well modeled. You bet. Don't forget, this is a rotating flexible structure in a fluid. Turbine testing is limited and expensive, and quite honestly, the people who manufacture these things don't want to do it. Okay, they want NREL to do it, and NREL does do a certain amount of it. But they want the federal government to do it. They don't want to do it themselves. Multiple resonances, we looked at a few of them, but there are lots more. Higher frequency stuff in the blades and in the towers. And of course the hydrodynamic forces that are also there when you have an offshore floating turbine. So that led us, Susan Frost and myself and my current students, to return back to an area that we've put a lot of effort into in the past for other applications, which is adaptive control. What we'd like is that adaptive control isn't going to solve all the problems, but we'd like that adaptive control can kind of put you in the right place. You could still have fixed gain controllers in this situation, but adaptive control would be there to kind of trim things up. So as you're in regulating in region 3, as you're tracking in 2, or as you're transitioning in 2.5. We'd like to keep things sort of calm. That's what we imagine that the adaptive controller is there to do. It requires a bunch of stuff. I've only got, I'm assuming you want me to end at 5 till the hour. Is that your normal thing? 5 till? So 10 minutes. I'm not going to cover all this. I'm sorry for that. I'd love to sit here and talk to you about adaptive control, because adaptive control is my big fun thing. But we started out in this a long, long time ago with distributed parameter systems, John Wynn and I, way back in the 80s. Rob Fuentes and I incorporated the idea of counteracting or mitigating disturbances into this stuff without having a lot of detailed information. And so at this point I was going to torture you with this, that a little theory break, but no, I'd rather be eaten by radioactive spiders, and here they are. So I'm not going to do that. I'm just going to try to say to you, adaptive control is not complicated. Okay? It isn't, but it is. It has some theoretical underpinnings that take a certain amount of effort to establish. But I think the idea that adaptive control is so difficult and so hard to understand and all the rest of that is just a falsehood. It's just completely false. I gave a talk at the IEEE Multi-Systems Conference, Adaptive Control, Will Adaptive Control Take Over the World? And my point was to try to show that adaptive control is not complicated. I don't have the time to do that with you, although it would be fun someday. But let me just say that this is the idea. Let me see, do I have anything else there on that slide? Yeah. What we're trying to do with adaptive control is we're trying to take a system, this one happens to be a nonlinear system that is smooth on a manifold, but doesn't matter. The idea here is we've got inputs and outputs that we can control this thing with. And what we're going to do is use only the outputs. Not any models, not any internal stuff here. We're just going to use the outputs, and we're going to try to suppress the output here. So if we could think of the output as, say, the delta in rotor speed, we want to drive that to 0. Okay? We want to do that without a bunch of modeling. Okay? So we want to do as much of that as we possibly can without having really complex models, which are kind of a bugaboo. All of you students here have been exposed, I'm sure, to Alexander Mikhailovich Lyapunov, and maybe to Barbalat, who nobody knows anything much about. But this is sort of the standard thing in Lyapunov theory, is that you have a nonlinear system, you have an energy-like function that's positive everywhere but 0, or at least positive inside of a manifold, 0 at 0. And now we have this V dot, this gradient story. If it's strictly negative, then everything is asymptotically stable. Everything would work. Okay? And in your classroom, you always see examples where that happens. And in reality, you never do. Okay? That never happens. It's so rare that it isn't worth really talking about. And so you need something that this fellow Barbalat came along with. First of all, if we have V dot less than or equal to 0, at least all the trajectories are bounded. Sometimes people are willing to stop there. That, to me, is a mathematician's answer. Okay? All things are bounded by 10 to the 14th. Okay? So I think it's a good stepping stone. It's a good place to start, but it's not what you really want. Barbalat comes along and says that if you've got something called uniform continuity, again, don't worry about the technical stuff here. Those of you who know it, know it. The rest of you, it doesn't matter that much. The idea is that you can drive certain things like the V dot to 0. And and then that will drive X to 0. What I claim is that no matter how you approach adaptive control, you always come to the same place. It always arrives at the same thing. So people can have real fancy things with learning and all that sort of stuff and fuzzy and all. It always arrives at the same control laws. Okay? You could almost say, well, let's just start there and see if they work. But it's also useful to know, is there some theory behind this? You know, I mean, I feel better, like when you fly something in space, you don't want to say to them, oh, by the way, when you're on board this thing, we don't actually know if it's stable. But have a fun ride. You know, that's just not the way that people want to do things, even if they're astronauts. So all roads lead to Rome. Actually, they don't anymore. I mean, you know, this is anybody who's been to Rome, you know it's a confusing rat's nest of roads. But they used to all lead to Rome. Rome was the center of the universe. And so this result that comes up here is a result that anybody and everybody gets in some form or another. And it just says we use a kind of a minus a quadratic here in the output, and that is, we integrate that, and that gives us the gains. So the gains are working against the outputs. What happens here, if y ever goes to 0, the gain stops adapting, and we're where we should be. We're regulated. If things change, if we develop an error there in y, then the gain begins adapting again and begins trying to move away from that with a minus sign. And that's essentially direct adaptive control. And there's some adaptive gain weighting that you can mess around with here. And I think, oh yeah, this is one of the bugaboos, though, is there isn't a rate of convergence. All of us engineers need to know some idea of, like, how fast do things converge. Again, if things converge, we say, oh yeah, everything is asymptotic. But again, if we have to wait 3 years, okay, it is asymptotic, but it's not very useful. Okay, so you need to have some idea of rates. And this is somewhat problematic in these Barbalat, Lyapunov-based things. Another route to take is this robust theorem, where you can say things will converge, but only to a neighborhood. In other words, they don't go to 0, they go to a neighborhood, but we can get an exponential rate. So this is some new stuff, and I'm not going to press on with that. For linear time invariant systems, again, if you know what these words mean, cool. If you don't, well, it's okay too. Fundamentally, you need something in the linear time invariant case that people call almost strictly dissipative. We do. So, it's equal to almost strictly passive in the linear case, but they're different otherwise, and almost strictly positive real. Let's go over here again, see what I'm talking about. But the good thing is that this thing in linear time invariant system is exactly equivalent to the high frequency gain is sign definite. Okay? So if you have multiple multi-input, multi-output systems, the high frequency gain is a matrix, so it has to be positive definite or negative definite. We'll just assume positive. And the open loop transfer function has to be minimum phase. All the transmission zeros have to be stable. That's the essence behind the linear version of adaptive control. Some things are different in the nonlinear case. Let's not worry about it. So here's two simple loop properties. This is why I say that, really, the theory is really not that complicated. You're looking at the high frequency gain sign, okay, which you may or may not know, and you're looking at the open loop transfer function. You don't have to know details about this. You just have to know the sign, SIGN, in the top case, and you have to have some idea that the zeros are stable. Keeping in mind that stability can be perturbed a little bit, so if you knew they're stable and you don't exactly know where they are, you've still got a little bit of room for everything to be okay. So when you connect an adaptive controller like what we talked about before, you're only going to get, let's back up 1 second, you're only going to get adaptive regulation if looking into and out of the system, the open loop has those two properties. And if they don't, then you don't. Okay? So what else can adaptive control do? I don't know. Does anybody even know who Sam Spade is in the Maltese Falcon anymore? It's all of us old timers, right? But anyway, I get, sometimes I'm bored by my own stupid jokes. The idea here is that you could, that now, for example, you could control persistent disturbances, which we talked about before, these persistent things like steps and sines and cosines. You could control them using the same essential adaptive control law, but what you need is you need a model basis for these disturbances. So if there's steps, the basis is 1. If there's sines and cosines, the basis is the unit sine, cosine, certain frequencies. You can have a lot of those. You could have a more complicated thing that was a superposition of a bunch of steps and sines and cosines. That would be a Fourier series or a finite Fourier series. So you could do this also. In other words, you can push this idea, and you can still do this. And in the regulator case, you don't need a wind speed measurement. Okay? So here's our adaptive control theorem that just says those things that we just spoke about before. And this minimum phase issue is there. Now what I want to do, and here's some simulation of this stuff. This is some of Susan's earlier work. I think it's in some journal somewhere. But the idea is just to say that the blue stuff is the adaptive, the black is a PI controller that was reasonably well designed here, and Susan likes to say we're doing better. 48% relative for improvement by adaptive. I'm not sure that that's really so essential, because if you could do it adaptively, you don't have to have somebody twiddling around there with a model for the next 15 years trying to get things to work right. Okay, so the adaptive has that benefit. Here's some other stuff about it. The pitch rates stuff. The pitch rates are slightly higher with adaptive, but they don't go through the roof. They're still acceptable. Here's turbulent wind flow, which is useful to look at. We haven't changed anything. Adaptive control is the same way. Blue is over here on this side. Blue is the adaptive, and black is the PI. Again, Susan likes the idea that, or used to, that this was 68% better, but that's kind of how you feel when you're writing your thesis or when you're trying to do, kind of your early work. It's like, my work's better than everybody. Cool, good, but it's not really the essential answer here. With about 60 seconds, I'm not going to be able to do very much with this region 2 thing, but I just want to suggest to you how we treated this from an adaptive point of view. We looked at the delta tip speed ratio that we're trying to track. Here's the operating one. Here's the one we're actually looking at. And we linearized it, so we have a kind of a tracking error here. And what this is saying is you're no longer looking at trying to drive delta omega t, which is the turbine speed, to 0. What you're trying to do is you're trying to drive this error between that delta and the delta wind speed. So in some sense, you're allowing some of the disturbance to come through into this, and you're tracking some of the disturbance, which is what we call this, disturbance tracking control. So we're output tracking, and we're trying to disturbance track this stuff. And here we need to know the wind speed. Okay? So this is disturbance tracking control. I'm just going to skip some slides here so you can escape fairly soon. And, but just to realize that there's a feed-through now that we're looking at. we're trying to feed through some of this variation in the wind speed. Because moving along region 2 is not regulating, it is tracking along this tip speed ratio error. So, I don't like the fact that you have to know the wind speed. From the very beginning of my work here in this stuff, I know that people measure the wind speed, but I also know that the wind speed measurements are pretty crappy. Okay, so I don't like that. So here what I've developed is a little wind speed estimator that fits inside the adaptive loop. It doesn't need to know anything about the plant. It just needs to know, what do you think that disturbance looks like? Is it steps? Is it sines? Is it cosines? Whatever. And because the wind speed things are either terribly expensive, which is LiDAR, or they suck. And so adaptive tracking involves introducing a disturbance estimator into the loop. Kaman Tapamagar and I have looked at this thing, and we have a new condition that is added to this thing. When the wind speed is not measured, we need more than that the plant in open loop is minimum phase. We need the plant multiplied in some sense by the error transfer function of that estimator. The product of those things has to now be minimum phase. And then everything works. Okay? And that leads to some new stuff. But like I said, that's the fun part of working on a serious application. Here's how it works with I think this is the 5 megawatt turbine, but I'm not sure. So you can kind of see actual wind speed, estimated wind speed. Starts out kind of not perfect, but gets better. Here's the tip speed ratio tracking, which is what we're trying to do for step wind. Here's turbulent inflow. And the bottom corner thing is how the wind speed estimator works with respect to the turbulent wind speed. You almost can't see the variations. There are some, but you almost can't see them. Okay, so it's pretty good. And here's the tip speed ratio being regulated quite well, around 7.5. Here's just a picture of something that I'm not talking to you about, which is adaptively transitioning from control in region 2 using fixed blade pitch and controlling the turbine, controlling the generator torque, and then moving through region 2.1 to transition to region 3, where we will control blade pitch and hold generator torque constant. So this is kind of an idea of what this looks like, and you can see that the adaptive wants to do it in a kind of a little smoother way than is normally done. We have another method for doing it, but it's not adaptive. Last but not least, LiDAR. You know, the issue about LiDAR is what I said, you've got to look out pretty far ahead of the turbine in order to see things. That means that you're going to introduce some fairly substantive delays in your control loop. Okay? Because what you see and what you're actually controlling are at different points in time. And so all I would say is this is an infinite dimensional problem, which makes my heart pound a little faster because I do that kind of stuff. Jack Hale, you want to know about delays? Read Jack Hale. Don't read anybody else. Okay? It's a waste of time. Don't read anybody else. I'm telling you that for sure. Read Jack Hale. Jack Hale knows what he's talking about here. And I came along and said, well, you need some kind of little slightly variant version, infinite dimensional version of Lyapunov-Barbalat. And so I stuck myself up there with A.M. Lyapunov. You can see he's not very happy about that. And probably rightly so, because I didn't do anything nearly as phenomenal as his work. Last thing is minimum phase. Lots of systems aren't minimum phase. This is not a wind turbine, but if you were looking at a launch vehicle, or if you're looking at sort of balancing a sloshing thing, you can see what non-minimum phase means. I push forward, and normally we would think that that would cause a forward motion, but in fact it causes the thing to topple back. That's the non-minimum phase behavior. When that's there in an adaptive system, the adaptive system does not know what to do. When it's in a modeled system, you typically would model, and you would say, here's my non-minimum phase plant, and here's how I want you to behave. But the adaptive system is really discomforted by the thing. Here's just a quick thing. Don't expect you to really get the whole deal. But we sort of use this idea of a filter and try to filter out of all the resonances, filter the ones that are non-minimum phase. Okay, try to filter them out. And wind turbines are non-minimum phase devices. Everybody's got a lab. I actually don't have a lab. But John Naughton and I do have this experiment on Flow control that DOE is supporting. Here's some stuff that we're doing on time-varying periodic plants where we're moving the airfoil in the flow to simulate it rotating. And we're using the Beddoes-Leshman model of that stuff. And Nailu Lee, my student, is doing some good work on that right now. So why should I care about this? Wind turbines are highly nonlinear, very poorly known dynamics, interact with exceptionally unsteady aerodynamics, especially offshore turbines. Extensive turbine testing is expensive and not attractive to industry. Not easy to collect good wind data, very little wind tunnel information. Turbine lifespans are not great. And some turbine flex dynamics are non-minimum phase. And so no detailed flow dynamics, and so this really falls into torturing adaptive control. This is like a real test bed for adaptive control as we progress along. So I'm going to end with the following thing, if I can get my cursor to work on this. Here's adaptive control in action. This is Hannah Robertson, the daughter of one of my former students, Robbie Robertson. Now let's see if it'll play. Oh, it's not going to play on your machine, is it? Well, that's too bad. It plays on my machine. That's why we should have used my machine. Hannah moves in here and moves the garbage can lid up and down a little bit, and then realizes that she has to adapt so she can make it close. Okay, and it's really very pretty. Sorry, I don't have that clever thing. Thanks so much. Kind attention. I know I've run over by about 5 minutes. I'm sorry for that. But thank you for coming, and appreciate it.
Do we have questions for our speaker?
Can we hang around here a little bit past the 11 o'clock time?
I have a quick question.
Sure, yeah.
I just wanted to hear your opinion on this. Since you mentioned about offshore wind,
Yeah.
and you put them way out on barges, floating barges. I'm an electric power systems engineer, and the thought is, how am I going to draw those lines back into the land? And where is my substation? Is it going to be a underwater substation, like a submarine, or the Neptune project? So I just wanted to hear your thoughts.
Yeah. I wish I had an answer for this. The magic answer to this would be, everybody would flock to wherever we are. Obviously, underwater things, more losses in the lines if they're underwater. Putting substations or maybe floating them on barges have its own problems. The only thing I would say is, at this point in the development of wind energy research, that's a good research topic, but I wouldn't want it to be the thing that impeded consideration of actually being able to operate turbines fairly far offshore in barge locations. Because I believe that's the kind of things we in universities are supposed to be paying attention to. I would say, if Pacific Power or whoever want to think about anchoring these things, a few meters offshore or whatever, that's not going to turn into the most complicated new thing. We need to be able to look out beyond this, and probably somebody, perhaps you, Sid, have to be thinking about this issue of transmission. How would that be done? I know that there are people with some kind of new ideas in this direction, but I haven't really followed them. Yes, sir.
Just a comment. We did work with offshore floating nuclear power plants back in the late 70s, early 80s, and they were doing a similar thing. They were placing nuclear power plants on barges far out in the distance, so you'd see this little dimple in the distance. And they had to deal with the same question of how to get power.
How to get power back.
One thing that they dealt with that you might have to worry about for offshore wind power is that once you put something out there, it becomes the responsibility of the Coast Guard. And you will not believe the incredibly weird requirements that the Coast Guard can put on things in terms of navigation hazards.
Yes.
And they were suggesting that these barges, which were inside berms for floating nuclear power plants, they would have to withstand like 30 feet of rime ice on the top of them, which would cause them to turn upside
tip
down
over,
and still be safe in those circumstances. And I can imagine similar things. By the way, Hieronymus, back in the 1950s, a professor at the University of Massachusetts, proposed offshore power plants where he was using the hydrogen fuel economy. And his idea was that the power plants would take seawater, turn it into hydrogen, and then these would be pumped ashore from storage containers, re-put together on land, and generate pollutionless
Yeah,
power.
not impossible. It's fairly expensive, but of course the renewable energy is cheap. But
The reason they went to offshore power in those days was interesting. He was very excited about building large wind power plants in New York and Massachusetts. And he happened to describe this to a friend of his who was in the Audubon Society. And after he had described the number of towers to him and where they would be placed, his friend said, "I will fight you to the death."
yes, yeah,
And he said, "Okay, I don't want to get into that
yeah,
argument."
yeah.
And he decided to see if he could get them offshore.
You know, all of these things, and thanks for the good commentary on this issue. All of these things are things that we as engineers in any energy field will have to face. You know, we'll have to face various versions of, can you really clean up coal? Okay, can that really be done or not? I mean, you know, is that just a fantasy? You know, does anybody want to build dams any place and any more rivers? No. You know, so where will the energy come from? I mean, we need it. Everybody wants it. You know, it's not like anybody, like I said, nobody's turning off the washer and dryer. Nobody stopped making the coffee. And industry needs it desperately, you know, if we're going to continue on. So some of this just has to be worked. There are always trade-offs. Engineers are the ones who have to deal with this stuff. I think when you start dealing with, say, the Audubon Society, no nasty comment about them, but when you start dealing with people who have one single issue, you're not going to get past that. You're going to have to deal with the whole trade-off picture. And we're used to that. We've been doing that, probably all of us, all of our lives. Anything else?
Questions, comments?
You've been a really kind audience. I appreciate it. Thanks so much.
Thank you. Before we leave, I have a couple of comments. One, I forgot to mention our co-sponsors with crew for this seminar series this semester. It's the School of Global Environmental Sustainability at CSU, that's SOGIC, so thanks to them. The next seminar in the Blue SOGIC series for this semester will be on March 9th, 10 a.m. same room. If you're joining us on the web, we'll provide you with the web link. And that will be by Professor Wade Shaw at the University of Nebraska. So thank you once again.
Take care.
Thanks for the talk.
Good to see you again. Yes, sir.